small eyes, so the small eyes will use all the internal stuff. I'll use small eye first. If any extra eyes, I'll use the big eye, but just for the extra eye stuff. Like I said. Okay. So we're almost done. We got through the first two layers of the eye last time. So we've got one more layer left. And if you open up the inside of the eyeball, you'll notice all the pink area there. That's going to be the innermost layer, innermost tunic, which is the sensory tunic, which is composed mostly of the retina. The retina is where all your photoreceptors are going to be. Your photoreceptors are the light-detecting cells, photo meaning light, and receptor. Now, one thing about the photoreceptors, they're actually not neurons. They are modified cells that detect light. So they're technically not neurons themselves. But for that signal to get to the brain, it needs a neuron to get there. So basically, the photoreceptors will tell the sensory neurons that then go down the optic nerve into the brain. You have two types of these photoreceptors, rods and cones. They both detect light. They just detect a little bit different kind of light. They're named for their shape. Rods are like rods, cones like a little traffic cone. They both detect light, but different kinds of light. Of the two, the rods are like the worst ones at detecting light. They really just say light is there or not. If light is there, it's white. If light's not there, it's black. And any shade of gray in between for like amount of light. So it's more your gray, your black-white vision, the gray vision. Your cones are your better light-detecting photoreceptors. They also detect color. So cones are color detecting, C for C. You have three types of cones when it comes to color: red, blue, and green. That's actually it. You technically only see in red, blue, and green color. To get like the yellows, the purples, the browns, the oranges, your brain will combine the different colors to make that. It's like you would mix paints to get a certain color. Your brain does the same thing with those three colors of cones. Your cones are also for what we call your high acuity vision. And your high acuity, that should be a dash, not a zero. High acuity is basically your high definition vision. So if you look like directly at the corner of the table, you can very clearly see it's a corner. Like it comes to a point, there's edges. But if you look at the table edge from your peripheral vision, it's very blurry. That's what high acuity means. It's your sharp vision, you're very detailed, where you see all the borders, all that. That's your sharp vision. That's your cones. Rods are the more blurry vision. They're really only good, like I said, yep, light, no light, and that's about it. Where these photoreceptors are going to be all the way at the very back of the retina. Like I said, they are not neurons, so they cannot send signals into the brain. So there's a few cells in the light pathway from the retina to the optic nerve. The photoreceptors detect the signal, or detect the light, They will then tell the bipolar neurons, that then tell the ganglion cells, which are neurons as well, so ganglion neurons. It's these ganglion neurons that then become the optic nerve and send the light to the vision signal to the brain. We can see the axons of those ganglion cells in the back of your model. Notice there's this big white spot there. I think it's yellow on the big model. You see all these red and purple strings going into that white little circle there. Those are the axons for the ganglion cells that then become the optic nerve, number 2, that goes into the brain. Where they're going into the optic nerve there, that white little disc there, that's called the optic disc. That's just made of axons of the ganglion cells. In other words, there's no retina right there where the optic disc is. What does that mean about the vision, or your vision where the optic disc is? Well, there's no retina. What else is there? Nothing there. There's no photoreceptors there. They're only in the retina. Your optic disc is your blind spot. You actually have a blind spot in both eyes where you literally cannot see anything because the light hits the optic disc, which is not the retina. So you're actually blind right there. You, of course, don't notice a blind spot in your vision for kind of two big reasons. One, we have two eyes. So the left eye's blind spot, the right eye can see, and vice versa. But if you close one eye, you still don't see a blind spot. So why is that? Your brain fills in the blind spot with what it thinks it's there. And it's very good at that, right? You can look at your surroundings, you can figure out, oh, well, if all that around there is brown, this is also probably some brown spot or whatever. The blind spot's also very, very close in front of your face, as well as another reason why you can't see it. It's barely in front of your nose right here, in front of each eye, so nothing very important there. You can find your blind spot. There's a little test you can do at home. Just Google it, like blind spot test for vision, not the car, obviously. You basically take a piece of paper, you'll put two dots, I think it's about an inch and a half apart. You'll put one dot in front of the eye you want to look at, close the other one, and slowly bring it back. Eventually, this medial dot will disappear. And that's your blind spot. It's about like 7 centimeters, 2-3 inches in front of your face, right by your nose. So, yeah. That's when light would hit the optic disc. You can't see them. Then, to the side of the optic disc, we have these two structures here, the macula luteae and the fovea centralis. On the small eye model, that's the little red circle with the yellow dot in the middle. On the big model, you'll have a yellow circle with an indentation in it. That's the thing there. The entire red region, including the yellow dot, that's the macula. The center of the red circle, that yellow dot, is the fovea centralis. Now, in the actual eye, you cannot actually see the fovea. The macula is just a darker spot next to the optic disc, and the middle of that is the fovea. It's not a separate structure, it's just the middle of the macula is the fovea centralis. The macula and the fovea is where you see the best. It's your best vision because that's right in front of your eye, basically. When you look directly at something, you see your best. That's because light is hitting the macula and the fovea, where most of your cones and rods are. That's your best vision. For the most part, rods and cones are spread everywhere in your retina. Right? You can see on your peripheral vision, you see color there. You might notice, if you look at your peripheral vision, the color is not as clear as when you look directly at something. That's because most of your cones are in your macula. There's some in your peripheral vision, it's not a lot. You don't see color as well. Most of your cones are going to be in the macula and the fovea. You have some rods in your macula, but there are no rods in the fovea, in the middle of it. It's just cones there. Question on the retina, bro. One of the most common reasons for vision loss as you get older is something called macular degeneration. That's when the macula starts to break down. This is like, if you go to the optometrist, they take the picture inside of your eye. That's basically what they see. You actually do have a little glowing spot. That's the optic disc. We can also tell because that's where all the arteries, veins, and axons are going into. Right by it, that darker region is the macula. If it's going away, degenerating, then it'll just be getting smaller and smaller and smaller, leading to a blind spot in the middle of your vision. That's something to be done. Any questions on? So that's all the main parts of the eye we're going to discuss. But now let's talk about how you actually see. How does light get to the photoreceptor so you can actually see? So if you see something, light has to hit the retina. Well, when we talked about the fibrous tunic, the sclera and the cornea, we said that light cannot pass through the sclera, it's got to pass through the cornea. The same thing is true for a lot of this stuff. There's a specific pathway light has to travel to get to the retina. If it doesn't follow that pathway, the structures block it, so you can't see things. How light travels is in straight lines. So, light travels in straight lines, but we want to make sure as much light as we can hits the macula, because that's where we see the best. So in order for us to get light to the macula, or the retina in general, we have to bend the light waves. And that's called refraction. Not reflection, refraction. Refraction is like when you have a glass of water with the straw is over here outside the water, but in the glass, the straw is over here. That's refraction. What caused that was the water and the glass bent the light at different angles to make it look like it's coming from over here instead of where it should be. You do the same thing in your eye. There's 4 structures in your eye that as light passes through them, bend the light a little bit so it can try to hit the macula. Anything that's not air is going to bend light in terms of our eye. So as soon as we pass through something that's not air, light's going to get bent by that thing. So first thing we hit has to be the cornea, because we can't pass through sclera. So we're first going to hit the cornea, and that's going to bend the light. We pass through the cornea. Now we're in this space here, which is filled with the aqueous humor. Well, aqueous humor is not air, so it bends the light too. Then we have to pass through the pupil, because we can't pass through the iris. The pupil's a hole, so nothing's going to bend there. But then we hit the lens. The lens is the third thing that bends the light. And finally, we pass through the vitreous humor, and that's the last thing. So cornea, aqueous humor, lens, and vitreous humor, those are the 4 things that bend, refract the light as it passes on its way to the retina. And this has to happen. These things have to bend the light a certain amount so it hits the right parts of the retina. If it doesn't bend it correctly, you can't see well. And that could be a reason you're either nearsighted or short or farsighted. The stuff in your eye isn't working right. It's not bending the light enough. Maybe it's bending it too much, so you're not seeing like you should see. Now, a lot of people think the lens is the strongest when it comes to the bending power, because we know the lens is so important. The lens is important, but not because it's the strongest. The strongest of the 4 things that bend the light is the cornea. The first thing light hits is the strongest thing that's going to bend it. It has 2/3 of the entire bending power of the system. So the first thing light hits is the cornea. It's going to bend it 2/3 of the way. The aqueous humor, lens, and vitreous humor bend it the other 1/3 of the way. The second strongest is the lens, but the strongest is the cornea. Now the lens is very important in the pathway though, but not because it's the strongest, It's important because it's the only one that can change how strong it is. Cornea, aqueous, and vitreous humor are always the same strength. It's the lens that can change its strength, which I mentioned before. When these suspensory ligaments pull or relax, they pull on the lens, which makes the lens get fatter and skinnier. And that process is called accommodation. Accommodation is the way the lens changes the shape to look at something far away versus up close. This switch happens majorly at about 20 feet away. That's why the base point for our vision is something over 20, because that's the lens working closer and further from 20 feet. You kind of feel this working. Yeah, so you in the front, look at the back wall. Yeah, on the back, look at this wall. Look at the wall far away from you. Put your hand in front of your face like this and focus on the wall. The wall should be clear, your hand's blurry, right? Now switch. Now your hand's clear and the wall's blurry, right? You don't have to really do much, right? You just have to switch your focus. And what happened in your eye is your lens went from this, skinny, looking at the wall, to fat when it's looking at something close to your face. That changes how strong the lens is, bends the light more or less, more when it's close, less when it's far away. That's a combination. If you do it very quickly, you might actually feel like something in your eye is contracting. Something is, you have a ring of muscle here, that ciliary muscle is contracting and relaxing to pull the lens to get fatter or skinnier. You might actually be able to feel that. Question on the eye. Next, we're going to look at the ear, which is a lot bigger than people think. A lot of people, they say the ear, they're just talking about this thing on the outside. That's part of the ear, but the ear is everything from here until we get to these little structures inside the temporal bone. So it's a lot bigger than people think. We separate the ear into three regions: the outer ear, middle ear, and inner ear. We'll start with the outer ear. The outer ear, of course, starts at the outside, this big thing of cartilage and skin. It also includes the tube, and it stops at the eardrum. So everything missing outside the eardrum is the outer ear. What most people call the ear, its correct official name is the auricle or the pinna. Either is fine. It's just the outer structure here. This tunnel here, you should already know what it's called because we already learned about it when it comes to bones. This is the hole in the temporal bone. This is the external auditory meatus, external acoustic canal. Again, whatever combination you want to go with, like for the bones, it's fine here as well. And then we end at the eardrum, which we need to call the tympanic membrane. That's its official name. So the outer ear is made of the auricle or the pinna, the external acoustic canal, and then it ends at the tympanic membrane. Questions on the outer ear structures? Let's look at the function of each of these. For the most part, until we get to the cochlea at the very end, the function of all these ear structures is just to transmit sound out of our ear to inside. Now, light traveled in straight lines. Sound travels in waves that are basically pressure waves. Have you ever seen like a video of a jet airplane breaking the sound barrier? That big shock wave you saw come out, that was the sound. Sound is just pressure. So with this big auricle, this pinna is far. We can see what's far if we make it bigger. So if you cut your hands around your ears like this to make your auricle bigger, you should notice I sound louder. Because that's the function of this thing. It's the trap sound to funnel it into the ear. So the bigger it is, the more sound wave you can trap, the louder something will appear. So people with bigger ears should hear better than someone with smaller ears, assuming everything else is the same. The canal, very obvious, is just the tube that sound will travel through to get to the tympanic membrane. The function of the membrane is to turn the pressure wave in air into a physical vibration to start the rest of the pathway. Questions on that stuff? Function of each one. Little PSA, I'm sure everyone knows this point now. Q-tips are not used for everyone else uses them for. You should not put anything in your ear at all. Especially not Q-tips. We all do it. We're probably all going to keep doing it to clean your ears. Just be careful. You should not have to clean your ears. We all as well, by the way. You don't have to clean your vagina either. Both your ears and vagina are self-cleaning structures. They clean themselves, which kind of makes sense, right? We didn't have Q-tips back in the day, caveman time. The ears were fine. Your ears should be self-cleaning. There are some conditions where you do produce too much earwax, in which case there are little drops you can buy that break down the earwax. You can also basically make this solution at home. If you take a little cap full of hydrogen peroxide with an equal cap of water, mix that together, let it get to room temperature, those drops will break down the earwax as well. You just basically let it drain out with a little paper towel in your ear. Do not do the little earwax, the candle wax thing in your ear. It does not work. It actually causes more damage and doesn't work at all. Don't do that. Another reason why the Q-tips are bad, besides you might pop your tympanic membrane, they're made of cotton. Cotton's very rough. If you keep doing this on your skin with your cotton shirts, it's going to scratch your skin. Your ear is also skin. So you're basically exfoliating your inner ear, very sensitive skin, with cotton, causing little micro tears, which could cause infection. Also, Q-tips are not good at getting earwax out. Most Q-tips just push the earwax further in, which can cause what's called compacted earwax. Basically, earwax pushes up and sticks to the membrane to where the membrane can't vibrate. Now you can hear it because this has to vibrate for you to hear. And if you have compacted earwax, you have to go to the doctor and have to actually scrape it out carefully with the little metal thing. Just be careful. If you actually burst your eardrum, you pop your tympanic membrane, that's it. It can't heal. If it was like a little tiny puncture, like a microscopic puncture, it can fix that a little bit. But if it completely ruptures, your body has no way to fix it. It cannot fix your tympanic membrane if it ruptures. We've luckily basically just gotten to the point within the past few years we can make synthetic tympanic membranes to go put in. It's surgery though, probably very expensive, so better off just not causing any damage to it. But that's all the outer ear stuff. After the tympanic membrane, we're then going to enter the middle ear. The middle ear is extremely small. Very, very small. It's just everything after the tympanic membrane in this little space here. So just this little tiny space between the tympanic membrane and the bones. Here's your middle ear. This tube is also part of the middle ear, but once we're inside the bone, the temporal bone, that's inner ear. So this is a tiny spot, there's the middle ear. The major structures of the middle ear are the three smallest bones in your body, what we call your auditory ossicles. Ossicles comes from the word oscillate. Oscillate means to vibrate. So the function of these three bones, 1, 2, and just this little tiny part there, the little horseshoe there, their function just is to vibrate. You'll notice the first bone is actually connected to the tympanic membrane. This first bone here, number 8, that's got this little spike on it, this whole thing, This is called the malleus, like mallet, malleus. We call it a mallet or the malleus because it looks like a mallet, like a little hammer that hits the second bone, number 9. That's got looks like a little axe, right? That's called the incus.
Incus is 9.
Yes. So the malleus, number 8, hits number 9, the incus, makes it vibrate, which sends vibration down this little foot here to eventually vibrate on this bone here we call the stapes. So basically the tympanic membrane vibrates, that vibrates the malleus, which vibrates the incus, which vibrates the stapes. Transferring that airwave sound pressure into a solid pressure from the membrane through those 3 bones. Now the common terminology for malleus, incus, and stapes, they translate into hammer, anvil, and stirrup from Latin, but we need to call them malleus, incus, stapes.
So stapes would be the number
11, I think. Yes, 11. It's just a little horseshoe-shaped thing. Like, so stapes, as in stirrup, the thing you put your foot in for horse, because it looks like that. So I can show you.
Looks like a little wishbone.
It's almost there. Just exactly just like the whole machine. Again, stapes is for stirrup like you put your foot in when you're riding a horse. Yeah. The part of the middle ear structures, all these bones, is just to make a bridge to bring sound from the tympanic membrane into the inner ear, which is all these tubes and stuff that the stapes is attached to.
Question.
Yes.
On the picture, it's saying it's opposite. The May is.
Mouse is first then. Mouse is first then.
So this right here
Yeah.
is this.
So this whole thing here is the mouse,
Okay.
and this thing is this whole thing here.
Okay, I thought you said the opposite.
No, mouse is first. Yeah.
Okay. Thank you.
Malleus, incus, stapes, miss. Malleus, incus, stapes, miss. M-I-S. Before we get to the inner ear, there's one more structure of the middle ear. That's this tube here that leads to the throat. It's got 3 names. You probably know as the eustachian tube. It's also called the auditory tube. It's also called the pharyngeal throat tympanic tube. Any of those are fine. So eustachian tube, auditory tube, pharyngeal tympanic tube, all that's fine for this tube. Why do we have this tube? Why do we want the middle ear to connect to the throat? What's the purpose of that? You don't hear with your throat, right? So what's the purpose of that tube? Nope. You should have no fluid in your middle ear. If you got fluid in your middle ear, that's actually bad. But no, this is all air. There's no fluid in here, or there shouldn't be. Get close to vent. Remember, sound is pressure. As the pressure gets transmitted from the membrane here to the bones, it builds up pressure as they vibrate in the air and the space here. So this tube is to vent or equalize the pressure, allow the pressure to escape. Because if the pressure builds up, it can get so much that actually pops the eardrum from the inside, which we obviously don't want. If you get a lot of middle ear infections, this tube can swell up and inflame, leading to that buildup of pressure you might feel inside your ear. Actually, what happens? You actually are building up pressure in here, which, if you're not careful to alleviate it, can burst you from the inside. No, so the tubes, I think, go somewhere else. Yeah. I think they get put into the eardrum, I want to say. You ever flew an airplane and you go up or down, your eardrums might pop? Actually, don't. If your eardrums pop, it's not a good thing because they burst open. That popping sound you hear is just like in a pressure cooker, and you hit the pressure valve and you get that air that shoots out. That's what's happening. As you go up and down the airplane, the pressure changes. Going one way, it's the pressure going out. Other way is the pressure going in. That popping you hear is just this tube, the air rushing up and down the tube very, very quick. Some people think that hurts because this, again, is building up pressure. So they say, oh, you can chew gum to help it. It will, but not because of the gum. People think it's the gum itself that's what's doing anything. It's not. When you chew, when you move your jaw, it pulls down on the tube as well, opening up the tube. So it's just the moving, the opening of your jaw that's what's helping, not the gum itself. If you are someone who can like pop their eardrums and you can actually pop them, like you like make that little vibration sound in your ear, what you're actually doing is opening and closing this tube to change the pressure, and that's the pop you hear from that. If you can do that, you have an extra muscle that people can't and don't have. It's a vestigial muscle. Yes, but it's not going to change style, I don't think. So, let's see. No, so we're stuck here. The inner ear is the stuff inside your temporal bone. It's not something you can take out like this. It's not a separate thing you can actually go and take out of your body. It's just a tube network inside the bone, the temporal bone. There's just a bunch of hollow cavities inside the temporal bone that look like that if you could like chisel them out. Let's keep following sound. So sound came from the outside, tympanic membrane vibrated, that vibrated malleus, incus, and then stapes. If we could take the stapes off, there would be a hole that is vibrating over. We call that the oval window because it's shaped like an oval. And inside the inner ear, it's filled with the fluid. Well, if you would like have a cup of water and you take your hand and do this over the cup of water without moving the cup itself, you would see the water inside the cup start to vibrate. Because what you're doing is you're changing the pressure inside the cup of water by seeing that vibration pattern through it. Same thing happens here with the stapes. As the stapes vibrates, it vibrates over the oval window, which causes pressure waves inside the fluid in what's called the vestibule, this middle part here. For the sound, for you to hear, it's going to travel from the vestibule to the snail shell, which we call the cochlea. On the cochlea side, there's a lot of words like the organ of Corti, the cochlear duct, all that. Ignore it, just know cochlea. It's the snail shell. Inside the cochlea, you have cells we call inner ear hair cells, because they're cells that look like hair in your inner ear. They're not actually hair, though. They're just cells that look like a piece of hair, so we call them hair cells, but they're not actually hair. There's basically cells that are standing up. If you imagine you would be in a pool of water, and all of a sudden the water, like or you're in the ocean, you had a big wave coming at you. What's going to happen to you as that wave hits you? You're going to move, right? You're going to feel the force of that wave. Same thing happens in the cochlea when that pressure waves comes through it for the hair cells. As that wave we're making by vibrating the stapes transfers to the vestibule and then travels down the cochlea, the wave is going to bend the hair cells. That's what hearing is. The bending of the hair cells is what we register, or what your brain registers as a sound, as hearing. The stronger the wave, meaning the louder the sound, the more the hair is going to bend. So the more hair bends, or these hair cells bend, the stronger, the louder the sound is. The less they bend, the quieter the sound. Another thing we can register though is pitch. That's the frequency. That's how fast the hairs are vibrating. So if the wave's going really fast repeatedly, that'll be a higher pitch sound. If they're bending very slowly, that's a lower pitch, a deeper sound. But hearing in general, everything about hearing is all about how are the hair cells bending inside the cochlea. Question over on the pathway of sound. Now, it's one other thing your inner ear is for, and that's what really the vestibule is for, and these canals here we call the semicircular canals. These two structures, the vestibule is just a thing the stapes goes into, and these semicircular canals are for your sense of balance or equilibrium, like physical balance, how you don't fall over. You have two types of balance. Each is picked up by the canals of the vestibule. The vestibule is for your static or stationary equilibrium, meaning your body's not physically moving, you're not walking, you're not turning. Maybe you're standing up straight or maybe bending. That's your static, your stationary equilibrium. How this works is that inside the fluid here, forgot to mention, the fluid in the inner ear is called lymph. You're going to learn in AP2 about the lymphatic system, which also has lymph. It's not the same lymph. Lymph just means fluid in Latin. So it's just a fluid. We kept the name lymph for it. It's different lymph though. Inside the lymph in the vestibule, you have a bunch of rocks. We call those rocks otoliths, which just means rocks. So basically, if you imagine I had a tray of Jell-O with rocks in it on my hand like this, and I tip it this way, what's going to happen to the Jell-O and the rocks? Yeah, they're going to slide this way, right? Once I'm tipping this way, go that way, forward, it goes forward, back, it goes back. That's how your stationary equilibrium works. As you turn, the rocks in the lymph here slide that way. Your brain's like, oh, we're going this way. You turn the other way, you're going this way, forward, back, etc. If you like to do it over and over really fast, you might feel like a weight shifting around in your head. You are. That's the brain analyzing the shifting back and forth of the fluid and rocks, the otoliths inside the vestibule. Your other equilibrium, your other sense of balance is your dynamic or rotational balance. That's your moving balance. Like when you're walking, you don't fall over, how you can spin around or turn and not fall over. That's the job of the semicircular canals, which are also filled with fluid. Where the canals meet the vestibule, you'll notice it's a little bit thicker. Those thicker parts where canal meets vestibule, we call ampulla. Inside the ampulla, you have a big pole sticking up that can bend. If you imagine the ampulla is right there, if the water in the canals is going clockwise, that's going to bend the pole one direction. But if the lymph goes counterclockwise, it's going to bend the other direction. You have multiple of these ampullas, some bending up and down, some left and right, some like front and back. So as the water moves in different directions, as the lymph moves in different directions through the canals, your brain takes all the different directions of the movement and knows you're moving forward, you're turning left, you're turning right, etc. This is the one you've probably experimented with as a child when you spun really fast in a circle. So if you imagine you're in a swimming pool and we all decide to run in a clockwise direction inside the swimming pool edge, well, let's come to the water. It's going to come with us, right? We'll make a little whirlpool. What happens when you stop? The water keeps going, right? Same thing happens in these canals when you spin around really fast and stop. It takes a while for the lymph to slow down and stop. Well, your brain can feel, oh, our body has stopped, but these canals says we're not stopped, we're keep on going. So the brain makes up an image and you're stopped, but you still see your world spinning because the brain's like, well, we're obviously still moving. Let's make it look like we're moving still. That's what you feel when you're dizzy. If I understand it right, I think vertigo is more your stationary equilibrium. Has anybody ever had vertigo? It's when like you're sitting down, you feel like you can't, feel like you're dizzy, right? That would be your vestibule doing that. But one last thing to identify is going to be this nerve here. We already know what it is. It's the vestibulocochlear nerve number 8 because it comes from cochlea and the vestibule / canals for hearing and balance. Right? That's all the stuff. That's what we're done. Exam is on Thursday for us. Does anybody know they're definitely going to miss Thursday's exam? Everyone's going to make it? If not, let me know. You have to come tomorrow because we have no time for makeups because Monday and Tuesday are finals. I have to leave early on Thursday to go to the doctor's appointment. I have to leave at 3. Like we did for the last exam, though, I should be able to set up in here a little bit earlier. So you want to come a little early, like, 1:30? Might be done around there, leaving early. If you know you're going to need more time, try to do that. Have someone coming in at 3 to watch out for the last 15 minutes. If you stay after that's fine, too. I won't be able to grade y'all exams until later that day, probably Friday. You'll know your grade by Friday night, though, for this exam. The final is going to be Tuesday for us. If you can't make the final Tuesday, you got to come on a Monday. But that's no time for makeups. It's cumulative. It's only anatomy, though. So it's going to be 50 ID questions, no multiple choice. 10 of those questions are going to be tissue questions. So look at the tissue. What is it? No microscope. That's going to be on the little PowerPoint, like I had the first exam, rotating through the board. Stuff like with microscopes. The other 40 questions, expect basically 10 from each exam. So 10 like parts of the body questions, 10 bone, skin questions, 10 muscle, and 10 from exam 4. But it can be anything. And now we talked about can be on the final. It's optional though. So if after exam 4 is graded, after I put the bonus points in, which I'll do Friday if you haven't done them yet, if you like that grade, you're done. If you want to try to bring your grade up, you want to know what do I need to make on the final to go to the next letter, email me after I put everything in, like Saturday or Sunday. I was like, make this in the final. The grade goes up. If you don't, your grade stays the same. You're not going to go down. You only go up from the final.
Did you drop the lowest grade?
You got to take final. Yeah, I do drop the lowest grade. If you don't take the final, your final is your lowest grade, so the final drops.
Okay.
But yeah, take the final, do better than your lowest exam drops, and replaces the final. Probably that night, Tuesday, but my grades due Wednesday, so you definitely know by Wednesday that your final grade.
We have to let you know which ones to take.
Yeah, I'll probably will send an email out asking, just so I know how many people to expect, because I would love no one to be final. So I don't come do anything. But so I don't waste paper. I know how many people to expect. Exactly. So if I send that email out, if you are going to take it, respond. If you're not, just don't say anything. I'll just count the yeses, basically. So, the same thing for lecture 2. Be on the lookout for that. I think that's all I got. Any questions about exam for the final? Like procedural questions over there. If not, that's it. We still have 30 minutes left. So you want this the last chance you got to review for exam 4 or the final. There's no